arrangement of capacitors, and factors affecting electrostatics 2. In this topic, the following subtopics will be covered: types of capacitors, arrangement of capacitors, and factors affecting capacitance. In Form 1 Physics, we studied Electrostatics 1. In this topic, we further the knowledge we gained in Form 1 to include capacitors and their uses, among other things. Most electrical devices like radios, TVs, computers have capacitors installed in them.
Capacitors. A capacitor is a device for storing charge. There are various types of capacitors including paper capacitors, air capacitors, electrolytic capacitors, among others. The following animation shows how a capacitor works. Click on the play button and make your observations. Observation. When the switch is closed, electrons flow from the negative terminal of the cell and accumulate on plate B, making it negatively charged. At the same time, an equal number of electrons leave plate A to the positive terminal, leaving plate A positive. This accumulation of charges on the plates shows that the capacitor is now charged. Explanation. When the switch is open, the two plates have no charge. On closing the switch, charges from the negative terminal flow to plate B due to the potential difference between them. Likewise, negative charges flow from plate A to the positive terminal. Representation of capacitors in circuit diagrams. Capacitors are represented in circuit diagrams using the symbols below.
Arrangement of capacitors. The use of capacitors depends on their capacitance and the way they are arranged in circuit. Capacitors can be arranged either in series or in parallel.
Capacitors in series. We are now going to derive the formula for determining the effective capacitance for capacitors in series. The charge Q stored by the capacitors in series is the same. The voltage V across the capacitor is given by the ratio of the charge to the effective capacitance, denoted by V is equal to Q divided by CT. Therefore, the voltage V across the capacitors is given by V is equal to V1 plus V2. Thus, Q divided by CT is equal to Q divided by C1 plus Q divided by C2. By factoring out Q and dividing through by Q, we get 1 divided by CT is equal to 1 divided by C1 plus 1 divided by C2. The reciprocal of the effective capacitance is equal to the sum of the reciprocals of the two individual capacitors. Thus, the effective capacitance for this case is CT is equal to C1 multiplied by C2 divided by C1 plus C2. For any number of capacitors N, the reciprocal of the effective capacitance is equal to the sum of the reciprocal of the individual capacitances in the circuit. That is, 1 divided by CT is equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3 plus 1 divided by Cn. Capacitors in parallel. Play the animation below to see how charge moves when allowed to flow in a circuit by closing the switch. Derivation of effective capacitance for capacitors in parallel is done as in the following steps. Note that when the capacitors are in parallel, the potential drop across the capacitors is the same. Q is equal to Q1 plus Q2. Q is equal to CTV. CT is the effective capacitance. Therefore, CTV is equal to C1V plus C2V. Hence, CT is equal to C1 plus C2 for two capacitors in parallel. For n number of capacitors, CT is equal to C1 plus C2 plus Cn. Charging and discharging of capacitors. The following animation demonstrates the charging and discharging of a capacitor. Click on the play button to observe how this takes place. Observation. When the switch is connected to the cell, the voltmeter gradually deflects to a maximum value. This deflection is due to charge gradually accumulating on the plates of the capacitor. This process is known as charging the capacitor. When the switch is connected to the load, light-emitting diode, the voltmeter reading gradually drops to 0, and at the same time, the brightness of the light-emitting diode gradually decreases. Explanation. The reduction of the voltmeter reading and the decrease in brightness of the light-emitting diode is due to the discharging of the capacitor. Energy stored in a capacitor. The energy stored in a capacitor is the work done in moving a charge Q through a potential difference V. Work done is equal to the average charge multiplied by the potential difference V. How do we get the average charge? The charge gradually increases from 0 to a maximum value Q. Therefore, the average value of charge equals, into bracket, 0 plus Q divided by 2, which is equal to half Q. So, the work done, W, is equal to half Q multiplied by V, which gives us half QV. But Q is equal to CV. Therefore, W is equal to half CV to the power of 2. Also, V is equal to Q divided by C, hence W is equal to half Q squared divided by C. Factors affecting capacitance. Capacitance depends on the following factors: distance of separation between plates, area of overlap between plates, and the dielectrical material.
Distance between the plates. As the distance between the plates of a capacitor increase, the capacitance decreases. Play the animation below and make your observation. Area of overlap. When the area of overlap decreases, the capacitance decreases and vice versa. Click on the play button and observe how the area of overlap affects capacitance.
Dielectrical material. The capacitance of a capacitor depends on the material separating the two plates. For the same capacitor, different media will offer different values of capacitance. The following animation further illustrates this. Click the play button to observe.